You're probably really comfortable with drawing free body diagrams in a number of situations, but drawing free body diagrams and understanding how to use them when an object is on an inclined plane, like a surface at an angle, is one of the harder things to do. So I'd like to start with a simple introduction to how to handle the force of gravity when you have an object that's on an inclined plane. We'll get more complicated later, but for now, let's just start with the force of gravity. Here's this specific problem. It says, a 100 Newton box is atop a surface inclined at 25 degrees. Find the components of the weight vector which are directed parallel and perpendicular to the inclined plane. In other words, the situation is that we have a surface at an angle, something like that. In fact, it says the surface is inclined at 25 degrees. And we have a box sitting on top of that surface. And the box has a weight of 100 newtons. And we're looking for the components of gravity. Now we know that gravity does pull straight down toward the center of the Earth, so the force of gravity is definitely downward. But in these sorts of problems, it's helpful to notice that if this box is going to accelerate at all, it's going to accelerate parallel to the plane. So it's very helpful to reconsider our perspective. Now I'm going to go ahead and redraw this surface with the box. Here's the surface. Here's the box. And while force of gravity points straight down toward the center of the Earth, and normally we call that in the y direction, for these kind of problems, it's helpful to rethink about our y direction. Now that doesn't look straight down to me. Let me first redraw that. Straight down toward the center of the Earth. There we go. So normally that is our y direction. But for these kind of problems, it's easier to change your perspective and to think of parallel to the ramp as the x direction. We kind of like tilt the way we're looking at it, look at it on an angle. And it's helpful to think of this direction as the y direction. Since any acceleration that happens is likely to be in the x direction, it's just an easier way to solve these problems. So this problem wants to know, for this force of gravity, what component, excuse me, what component is parallel to the plane? What component is in the x direction? And what component is perpendicular to the plane? What component is in the y direction? So if you look at this, we're looking for how much of this vector is this way and how much of this vector is this way. So let me go ahead and draw in the components. Perpendicular to the ramp, or in this y direction, I'm going to call this the force of gravity in the y direction. And then going this way, parallel to the ramp, or in the x direction, I'm going to call that the force of gravity in the x direction. And this is my new x. I'm calling this the x direction and this the y direction. And again, some people like to call this the parallel to the ramp component, and some people like to call this the perpendicular ramp component. So I'm looking for sides of a triangle. And to get sides of a triangle, it helps to know an angle in the triangle, and it helps to know the hypotenuse of the triangle. The hypotenuse is actually given. It tells you the weight in this problem. The weight is 100 newtons. So you know the force of gravity. The hypotenuse in this case is 100 newtons. Another thing you need to know is an angle within the triangle, and for reasons I won't explain now, the angle of the inclined plane is the same as the angle between the force of gravity and this new y component. In other words, this angle here is the same as this angle here. So I'm going to go ahead and write 25 degrees right in there. And then it's really a simple right triangle. The y and x components are always perpendicular to each other. So I have a hypotenuse, I have an angle, and I'm looking for sides. The one thing that's a little weird about it is if you'll notice that if this is my angle, my opposite side goes with x, which is a little weird for some people. And my adjacent side goes with y. It's not what you're used to doing, but it'll work. So let's solve for F, force of gravity, in the x direction. That's my opposite side. And I know my hypotenuse and an angle, so I'm going to use sine to solve for that. So I'm stepping back. Sine of an angle is opposite over hypotenuse. The angle is 25, the hypotenuse is 100. Sine of 25 is my opposite side, force of gravity in the x direction, over 100, my hypotenuse. And again, x is weird that it goes with sine, but in this problem it does. When you finish this off and you solve for the force of gravity in the x direction, you get 42.3 newtons. So I can go ahead here and write 42.3. That's the component of gravity that's pulling it down the ramp. That's the component of gravity that if there's nothing else going on is going to cause it to accelerate down the ramp. And I also want to know this force of gravity in the y direction, perpendicular to the ramp. So in that case, that's my adjacent side, and I know the angle and the hypotenuse. So I'm going to use cosine of an angle is adjacent over hypotenuse. Cosine of 25 degrees is my adjacent side, force of gravity in the y direction, over my hypotenuse, over 100. And when I solve for that, my force of gravity in the y direction, sometimes called perpendicular, is 90.6 newtons. And so we know this value is 90.6, it's in the negative y direction. And this value is 42.3, it's in the x direction, based on how I define these axes. Now that gets us the answer to this problem, but just to look ahead a bit, the reason why we want to know the x component of the force of gravity is that it's what's pulling it down the ramp, in the direction down the ramp. And the reason why we might want to know the y component of the force of gravity is maybe we're looking for normal force, which in this case would be perpendicular to the surface, or always perpendicular to the surface. But you can see that might help balance this.